and an example of that was on my robotic Christmas ornament. I had a Christmas tree on a servo swinging, and simultaneously it was playing a tune. Well, those are two independent activities. In a small microcontroller like this, you don't have a operating system that can let you start tasks and such. So state machines are a decent way of getting multiple things to happen simultaneously. So let's talk about how you design a state machine. They're typically represented, you typically start with a state diagram where the circle represents a place where the program's waiting for an event to happen before it changes to a different state. So the program has the concept of an internal state, and perhaps the door might be opened or closed. And while it waits in that state, the outputs are unchanged. They're not changing. You could wait on more than one event in a state, and you can have multiple, scores of states. It gets hard to draw if you get much more than that. When an event takes place, a state machine exits the state and transitions to the new state, or it could transition to the same state. Sometimes you want an event to go back to the same state, perhaps with some output. So let's see. The archetypal state machine is the light switch there. It holds state, right, of on or off. Flip the light switch off. It responds to a trigger, push down, and it transitions to the off state and gives an output of light off. And then when you flip it back on, up again, the trigger is up, then the state machine transitions back to the light on state. States can have timeouts that fire if none of the expected events occur within a set time limit. So a typical use of that might be where you want to back your robot up for a certain amount of time and then start going forwards again. So you just time out in some state and then transition. So here's how you draw a state. This E. So here's a state name. It's state number 1. E: means on entry, do this action. You usually write the trigger or the transition condition next to the arrow or on the arrow between states. So this tiny wanderer has a couple of significant state machines in it. One is the cliff detection state machine. So one state is moving forward. The other is the trigger that exits out of that state is a cliff is detected. That moves to a state where it moves backwards and decrements a timer. On entry, it initializes a timer. The trigger out of that state is the timer expired, and then it goes back to the move forward state. How you implement that in C is pretty straightforward. You just do a switch. You have a variable like an int. I call it analyze light SN state, or analyze light state machine state. So switches on that. It only has two cases, two values of this state. So this is a two-state machine, and in there you want to have a condition that will cause it. You want to check for the trigger condition that will cause it to transition out of that state and to a different state. So in this case, proximity differential is the difference between the light, the photosensor reading from the A to D converter when the LED was on versus when it was off. If that's less than some trigger, then it changes the speed. It sets a backup time, and it says, notice in_analyze state machine equals 1. That's next state will be 1. It doesn't actually change the state right there, and I'll explain why in a minute. Or else it stays in the same state, and the speed is servo going forward. Case 2 is the backup state, where if it's reached the end backup time, then next analyze state machine state is 0, which will take it back down. and this thing gets called every loop, so every 50 millisecond or 20 milliseconds or so gets called repeatedly. So this is how you, here's the essence of, this gets called, this internal segment gets run every 20 milliseconds, and it calls the analog to digital converter state machine and the analyze light state machine, which is the one we just looked at. The analog to digital converter state machine actually has about 5 states, so, and it just, but nothing that's particularly decision oriented. It just goes around in a circle from turning the LED on to measure light with the ADC and then turn LED off to the next one, which turns the LED back on again, and then then the next ticket goes around and turns and measures the light. So it's about a 4 or 5 state machine. But the point I want to make is that because you're calling these 2 state machine functions every tick, every 20 milliseconds, they can be doing completely unrelated things or collaborative things, but they save you from having to go into a mode where you're thinking through lots of procedural code about, if this has happened and if that's happened, then I do this. So it's a nice way of decoupling independent processes. The last thing to point out is this: at the end of the repeated loop, you assign the state machine state, to what the state machine had computed should be the next state. The trick here is if you assign the state directly within the state machine, then when this state machine computation function is called, depending on the order that you have your state machines in, it may pick up a transitional state that you didn't intend in one of the other state machines. So it's just better practice to have it transition cleanly, have all of the states transition at once, and then you recompute all of the state machines again next time through the loop based on what the current state is. And that was as far as I want to go. Is there any thoughts, questions, discussion on state machines?
You should declare, if you have a subroutine that gets called over and over again, just make sure you declare your local variables as static if they need to maintain their value between
Excellent point.
locations.
Thank you, Dale. Excellent point. The
using
state
global
variable is not shown here. I've got it declared further up as a static, meaning that it won't get forgotten. If I were to put it in here as like an int analyze, as an int, it is not guaranteed to hold its value between successive calls to the analyze light SM state machine function.
Well, furthermore, it means something completely different if it's static in the function versus static, further
Outside in the global, okay, yeah.
Yep.
Yeah, if
Right,
you
it's
declare it static inside the function, it will retain its value between
Good point.
locations.
Right.
Yes.
The problem with not
Yes.
declaring static is the limited memory on these things. If you're declaring a new value every time you go into the function, you'll run out of memory. If you
Yeah,
just
put some
declare
on
the
static.
whole- No, that's not using static is what I said. So if
But
you're not
that's why
using
you don't
static,
want to use statics unless you absolutely need to know what it is.
Oh, no, it takes up the same amount of memory whether,
no, what I'm
No,
also
it
saying
takes
is that,
up on stack, which means it gets reused each thing, each
Right.
function you call.
if you use the new though, create a new one inside each of your functions, like, let's say you're concatenating a string together.
Now you're going into much more difficult code than what we're
Yeah,
using.
but I mean, let's say that you take the result of this and you add 2 numbers together, and that's a new variable. And you
That would
actually
be-
call it new.
Okay.
That would be like.
No, that's-
C++.
There's no new in C.
yeah, this is straight C.
But Okay.
No.
Never mind.
That's a
Don't worry
good
about
point, though.
it.
It's-
Don't worry about it. You
Um,
guys, when you run out of memory, you'll,
That's another
you'll
technique.
figure out what I'm talking
If it's
about.
global, is it created on the stack?
No,
No,
It's on the heap, right? Yeah.
no, it's not on the heap
no,
either, it's just in global
actually
memory.
allocated in
It's just
the,
allocated in the memory.
it's
Okay.
hard allocated.
And when you say static and it's global, all it does is hide it from other files, so it just
Okay.
makes it in
It
that
has two
file.
different meanings.
And then
You're right.
static, function static, it's again, it's not on the stack.
Correct. It's permanently allocated.
Okay.
Yeah, it's permanently
The other reason that you want to make these make state variables at least declared and initialized outside of the state function is so that you can initialize it to its initial value of the state
Start with
machine
Of course,
before the machine starts.
But in either case, you're reducing your range.
There's
Well,
some,
anytime you declare a variable, you
Well, I
reduce
mean,
your range.
if it was not static to the function, you're only using that RAM while the function.
If it's an automatic variable.
Yeah, it's
then-
automatic and it's allocated on the stack and then it goes away after the
Yeah.
function returns,
Yes.
which is not what we want.
and there's a little bit of a trick, which you won't run into with the tool chains we're talking about, but if you ever go to a new processor that doesn't have startup code and you're essentially really bare metal, then all this allocating things in globals and getting the values assigned and stuff is in your startup code. And if you don't have startup code that does that, then it's not gonna happen.
Yeah,
Then
your
there'll
variables
be
aren't initialized.
random numbers, they won't be
Right.
zeroed, they won't be
Right.
anything, so
Right.
you got, there's some magic code outside of main that does all that stuff for you.
So I think that's it. As I said, all of the, so these videos are getting posted in the tutorial section. Steve's made a page in the tutorial section of the website